Everybody, let's talk about standing waves. Now consider with me for just a second what would happen if I had a single voltage wave propagating to the right. So I'm going to write this e to the minus j beta z. So that's the phasor representation for a sinusoidal wave propagating to the right. So let's take a little snapshot of what exactly you could expect to see if I were to represent something like this a little more visually. So if I take the real part of this and sort of take a snapshot of it throughout space, you would see a wave that kind of does something like this. It goes down and it'll come back up like so, and then down like that. And if I were to animate this thing in throughout time, you would just see this thing propagating to the right as time progresses, right? And it would be moving at, say, whatever the phase velocity is for that particular wave. And it would have an amplitude here, like so. We'll draw this out. That amplitude, that little peak, sorry, that should be touching there, is exactly V sub 0. All right? So one word for this is called a traveling wave, in the sense that it's traveling to the right. So you imagine taking the magnitude of this thing, like so. I would simply get the magnitude of V naught, which if we assume this is a real value, I just get V naught, like so, because the phasor bit goes away. So in this sense, it's common to refer to a wave like this also as being a flat wave, because it has the same constant amplitude throughout all space, like that. So its phasor amplitude is the same everywhere because the peaks here would just skirt that little level there. So flat. All right, so far that should be pretty intuitive, but let's add a little layer of complexity to it. Suppose now I have another wave like so, V naught e to the minus j beta z, and I'm going to add another wave propagating in the opposite direction, and it's going to be equal and opposite. So I'm going to call it V naught e to the plus j beta z. So there's two waves superimposed on each other, just propagating into each other's faces and interfering with each other. So what you'll get is V naught times the quantity e to the minus j beta z plus e to the plus j beta z. Now you look at that, that actually simplifies by Euler's identity. You'll have the real and the imaginary bits. The real bits, the cosine bits, will add together, and the imaginary sine bits actually subtract from each other. So what you end up having is 2 times V naught cosine of beta z. It'll become a purely real valued function. So what do you see if you plot this thing and then animate it in real time? So let's go ahead and draw what you would actually see from such a wave. So here is x. So remember, you have one wave going this way, another wave going that way, and at some moments they will destructively interfere and you'll get nothing at all. But then at other points in space they're going to constructively interfere and you'll get a doubling of your amplitude, as you can see here. So if I take the magnitude of this, you'll notice what I would get is essentially 2 V naught times the magnitude of the cosine beta z, like that. So there's kind of two ways to think of this. I'm going to just plot the magnitude of this, where it will do something like this. It'll go down, and then it will come up again, and then it will go down, and then it will come up, down, and then up, down, and so on. And what will happen is, if you look at this in time, you'll see the waves sort of doing this thing like this. So the black here just represents the absolute value. The green kind of represents what you would see on the wave as you kind of animate it in real time, like this. Okay, so you would see these waves just sort of bouncing up and down. And these little points here would be called nodes. They just sit there, they will be 0 constantly. And this point up here is called an antinode. So you've probably seen this effect if you ever just played with a slinky and wiggled it at just the right frequency, you would see where some bits just go to 0 and other bits just wobble up and down at this large amplitude, which if you have two waves going back and forth will be double the amplitude like that. So because if you watch this thing in real life, it looks like it's just kind of standing there wobbling up and down without any energy moving one way or the other. So in that sense, you get what is called a standing wave. Okay, and again, if you've played with a slinky or done, taken some basic physics, this is something you should have seen before and should be fairly intuitive, okay? So let's do a third scenario. What if I have two waves moving on top of each other? So I'm going to write this as V of z is equal to V naught plus e to the minus j beta z plus V naught minus e to the plus j beta the z, where the magnitude of V naught plus is greater than V naught minus. So now we have this situation of two waves going over, but now one wave is stronger than the other. So the question now is, what happens in this scenario? What would I see if I were to kind of draw that thing in real time? What would its amplitude be throughout space? So what normally happens in the world of transmission line theory, this reverse propagating wave is going to be a result of some mismatch at a load. So I'm going to just add the extra condition here that V naught minus is equal to gamma times V naught plus. Because this is a common scenario. We have mismatched loads where I'm exciting it with one wave, and then the reflection due to the mismatch is going the other way. So it's very common to just assume that there's some reflection coefficient associated with this little wave here. So what I'm going to get is the following. V of z is equal to V naught plus, and then I'm going to get the quantity of e to the minus j beta z plus gamma e to the plus j beta z. So now what I care about, what I want to know is, what is the magnitude of this thing going to look like? Okay, so one little simplification I'm going to make here. I'm going to take this little term here and factor it out. So what I would instead get is V naught plus, I'm going to have 1 plus gamma e to the plus 2j beta z times e to the minus j beta z. So you notice I just factored this little term out, which when I take the absolute value of all that, the magnitude, the absolute values are just going to distribute to everything, and this guy is going to disappear because it has a magnitude of 1. So let's go ahead and work that out now. So what I will have is the magnitude of my new V of z is equal to, I'm going to get the magnitude of the forward traveling wave. And for simplicity, let's just assume this thing is real valued. We can leave it as a magnitude later. But if it's just real valued, I'm going to just stop drawing these little absolute values here. And then I'm going to get the magnitude of 1 plus gamma times e to the plus 2j beta z. Like so. So remember, this little term disappeared. And there should be an absolute value here, but we're not going to worry so much about that right now. And then I just get absolute values on this term here. So I'm left with this guy. So let's just do this so we don't forget. So you could plot this, you could do a bunch of algebra on this and figure out what this thing actually looks like. But we don't really care too much about the functional form of it. You can do that, or you can just let MATLAB crunch on this sort of thing and do all the complex arithmetic for you. But you'll notice just right off the bat, there's some interesting things that are going to happen. But first I need to make one last little simplification. Let's rewrite gamma as the magnitude of gamma times e to the j phi. So there's a little bit of phase shift here. So I'm going to get the following. Magnitude of V naught plus, and then I get 1 plus the magnitude of gamma e to the plus 2j beta z, and then e to the j phi, like that. So part of the reason I do this is because I don't want to have to worry about the fact that gamma is a complex number, and this phi here is kind of arbitrary depending on how I define my origin. So it won't really fundamentally change the nature of what's happening. So for kicks and giggles, let's just assume I've defined my origin at just the right place. So for example, you can imagine just adding a little z minus beta phi, something like that. So I would want to match these guys out here so that they cancel. So you just insert a little offset here, like z minus z naught, to negate this. So just shift your coordinates a bit is all I'm trying to do. And I will get the following: v naught plus times 1 plus gamma e to the plus j beta z, like so. Okay, so this is an interesting expression because you'll notice it's basically 1 plus this thing here that's kind of oscillating a little bit back and forth. So just intuitively, right off the bat, it will look close to, not exactly, but you should see something like the following, where here is my amplitude, v naught plus, and it's going to go here. And you can see how it's going to be plus, and this thing here is going to oscillate back and forth when I take its magnitude. So I'm going to see something that's going to be a little high, and then it's going to have a low like this. And it's not going to be perfectly symmetric, even though I might be drawing it. It may not necessarily be, because as again, if we let this thing approach 1, then you saw how it was symmetric, but it may or may not be, depending what values are in between. So why is this interesting? So again, we don't really care about the functional form of this. What we care about are the peaks and the valleys of this thing. So all we know is that this thing is going to wobble up and down between two extremes. So I'm going to just kind of write this as -1 to 1. That's kind of the extremes of what this little phasor term here can do. So I'm just going to calculate the maximum and the minimum in accordance with the maximum and minimum of this term here. So what you'll get is something like Vmax is equal to the magnitude of z, its maximum value is what I'm going to define it as. And it's what happens when I get a 1 here. So I'm going to have v naught plus times 1 plus the magnitude of gamma. And I'm just going to put in parentheses now because this is the peak value. Now I'm also going to define a minimum value in a similar way. So it'll be the magnitude of this, its minimum value, whatever that minimum here. And you're going to get v naught plus times 1, and that minimum occurs when this little phasor term here goes to a -1, so I just get 1 minus the magnitude of gamma. Okay, so that tells us, let's fix our focus a little bit if we can. There we go. Oh, there we go. Sorry. There we go. So we now know what the peak here, that's my Vmax, and I know what the Vmin is over here. So let's take the ratio of that. So Vmax, let's move here, divided by Vmin is going to be this guy divided by that. So you notice these two terms here are going to divide out, and you're just going to get 1 plus the magnitude of gamma divided by 1 minus the magnitude of gamma. And this little expression here in microwave engineering has a very special name, which you may remember from your last class, and that is called the voltage standing wave ratio, or sometimes just standing wave ratio for short, or as I like to say, VSWR. That's one of my old professors used to always call it that. Okay, and so this is an interesting term because it just kind of relates another way of thinking about the mismatch between a transmission line and its load, because you can see how there's this correspondence between given some magnitude for gamma, I have a VSWR over here. So for example, if the magnitude of gamma is 0, then that means there are no reflections and all my energy is propagating to the right, and I'll get a ratio of 1. So that implies VSWR equals 1. So for a perfectly matched load, my standing wave ratio is 1 because my maximum and my minimum is going to be the same. So if I have a gamma of equal to 1, sort of the opposite extreme, the perfect mismatch, then what will happen is this little term here goes to 0, which gives me a singularity, and you get VSWR approaches infinity like that. Okay, so there's this nice sort of correspondence between VSWR and your reflection coefficient. And I'm going to put up a demo video as well where I actually do a simulation of a wave striking a mismatched load. So you'll see two waves superimposed, the one incident and the reflected, and what you'll see is this weird sort of creepy effect where the waves sort of pulsate up and down. And it looks sort of like energy is creeping to the right. All right, and so that's this idea of a standing wave ratio. So you have a standing wave, but not quite. So a perfect standing wave means both waves have equal and opposite, or just equal magnitude, but opposite direction. So that would be the perfect standing wave. And then the exact opposite of the standing wave was the flat wave, or the traveling wave, where there was none of that interference happening. You just had the wave going all the way to the right. And then this VSWR here kind of tells you a nice little, assigns a numerical value to all of the sort of possible ranges in between. Okay, so remember, a traveling wave is just a wave that'll be traveling to the right. A standing wave, it'll just sort of stand there with the nodes and antinodes pulsing up and down. And then you have all this in between where you kind of have, you don't really have nodes and you don't really have antinodes, but you see this weird wobbly effect that's going on. And it's indicative of a mismatch in a transmission line when you get that creepy wobbliness happening. So again, look out for the physics demo of that and you'll see what that looks like in real time. Okay, but that is standing waves in a nutshell.